Okay, so when we were doing all this currency transaction and so on, what we noticed is that if our currencies are all divisible by the same number, they're all say multiples of 2 or multiples of 4 and so on, then any transaction that you can do using those coins will also only be multiples of 2 or multiples of 4, right? Okay, so let's just try and make things a little bit more formal or mathematical. So often when we want to try and put things on sound footing, one of the first things we do in mathematics itself is to try and make a proper definition. Okay, so let me define, and here the focus is on having very precise language for what we want to express. So we already understand what integers are, we already saw what integers were, so let me just assume we know that. So let a and b be integers. Okay, now let me make a couple of remarks here. Often we want shorthands for all these things that we write in mathematics. So we could express the same statement by saying let a and b belong to z, right? This was the notation we use for the set of all integers. So when we say let a, b belong to z, it just means let them be elements of the set of integers. So this is another way of saying the same thing in shorthand. And the other important thing to note here is if we just say it like this, let a, b be integers, it means we are also allowing for the possibility that a could be equal to b. Okay, so there are no restrictions here. It's perfectly possible that a and b are actually the same integer also. If we wanted them to be different, we would say things like let a and b be distinct integers, or let them be not equal, and so on. So at the moment these are possibly even equal numbers. We say, so here's the definition, we say that b is a multiple of a. So this is what happened when we were looking at currencies. Our coins were sometimes multiples of 2 or multiples of 4. So what does multiple formally mean? So we say something is a multiple of another integer if the following happens. I can find if there exists an integer k such that b is nothing but a multiplied by k. It's a product of a and k. Okay. Now again, here as you've seen before, we want shorthands, and there exists an integer k. This sentence can be abbreviated to there exists, so that's a symbol for there exists k in z. Okay. So we could abbreviate it like that. So we say b is a multiple of a if there exists k belonging to z such that b is a times k. Okay. So this is what multiple means. Now we also, if this happens, we also use other words or phrases to mean the same thing. If this happens, we also sometimes say this is another ways we can say that a divides b, or a is a factor of b, or a is a divisor of b, and so on. So these are all words which mean the same thing.
Also, b is divisible by a,
or b is divisible by a. So you can think of all of these as really being the same definition, just slightly different English words to speak of the same concept. Now, so that's the formal definition. Okay. Now let's just warm up and see if we can manipulate this definition in some reasonable way. So here's an example just to see if we can work with this definition. So suppose you're given that a divides b. So first example, if a divides b prove that the integer minus a divides b also. Okay, so you're given that a divides b, a and b are integers, prove that the integer minus a also divides b.
Okay, so I have to. So what does that mean? That means that there exists.
Right. So let's see what's given first, and let's
Okay.
see what we have to prove. So here's how we'll construct the proof. So what's given is that a divides b. Now,
Okay.
so let's do that. Here's what's given: a divides b. Okay, so as always, this is a bit too cumbersome, and we often want to invent shorthand notation for this. So the notation for a divides b is the following. So we write a, and sort of this vertical line here divides b. So we read it as a divides b, and this vertical line in the middle is the divides symbol. Okay, so I'm given that a divides b. What that means is, by
So
definition,
there exists an integer k. There exists k in z, I guess.
Correct. So by definition, this means there exists an integer, there exists k in z,
such that
a
into k is b.
So b can be written as a into k. So let me just write as ka.
Okay, but now we want.
So let's see what we want. So let's do this what we want sort of on the margin for now. Let's see how to. So we work backwards from there. What we want is to show that minus a divides b.
Yeah, so b is
I.e.
b is something into minus a.
b can be written as some number L into minus a. That's what I want to show. Okay, there exists. So let me write it correctly. There exists an integer L such that b can be written as L times minus a. Now what we want is to find that integer L. Okay, and what we have in our hand is what's given, that b can be written like this. So let's see if we can use this to find that integer L. So observe, if b is k times a, then I can also write it as minus k times minus a.
Right.
Right. So what that tells me is that this number L that I seek can be taken to be this number minus k.
Oh, minus k is also an integer if k is an
minus
integer.
k is also an integer. Okay, so let's do the following. Let's define L to be the integer minus k. K is an integer, so is minus k. Then observe that b is exactly the integer L times minus a. Now what does this mean? By definition, this means, so this implies, this implies symbol, this implies that minus a divides b. Okay, and that's the end of the proof. So sometimes we denote the end of the proof like this, little shaded box, to say that that completes the proof. Okay, so often, so notice as something else we did in the course of this proof here, which is sort of had this little margin for ourselves on the side, where we worked out what is it that we needed to prove, okay, and saw, you know, what we need to somehow construct, and then began again from what was given and somehow tried to construct that number. Okay, so this is a typical example of how proofs work. Let's do one more. So suppose I have slightly more complicated than the previous. So I am going to take three numbers a, b, c. So let a, b, c be integers. Okay, if a divides b and b divides c, then a divides c. Okay, now prove. This is the thing you need to prove. Okay, so again, it's a question of formally proving this, ensuring that you can get it just from the definitions. So let's do this. We've seen one proof, so this one's going to be easy. What does it mean to say a divides b? Implies, means there is an integer k such that b can be written as k times a. Okay, now let's do the same thing. B divides c means there is an integer L such that c can be written as L times b. Okay, and let's sort of write on the margin. So what is it that we want?
We want C to be something times A. So
C
there
to be
exists
something times A, right? I need to find that something, that number there. Okay. Now let's see if we can just get it from what we know,
right.
So we'll just use these two equations here to say C is nothing but L times B, which is our L times K into A. And now we are in good shape, because what that expresses C as is C is just LK times A.
You use the associativity of
So
multiplication
what I
there.
used here is the associative property of multiplication of integers. But having done this, what I've manufactured is that question mark here. I need to construct some number such that C is that integer times A, and I have done exactly that. So observe, since L is an integer, K is an integer, means that this number I've constructed, L times K, is also an integer, right? So I have constructed that integer. I can call it something. Let M be that integer. Let M be the product of L times K. That's an integer. And what we have finally done is written C as M times A. In other words, we have proved that A divides C. Okay. So notice that all these are probably very familiar facts from actually working with numbers. Right? If I sort of give you numbers, you sort of know that if this divides, if this is a multiple of that, the third number is a multiple of the second number, then from experience you know that the third number is a multiple of the first one. But what we are focusing on here is in trying to prove it formally by carefully working through the definitions themselves. Okay, and that's a very important part of mathematical proof itself.
So then we really understand why it's true.
Right, exactly. Okay, let's do one more example of proof. So I again give you three integers a, b, c. If a divides b and a divides c, then prove that a divides their sum. Okay, note the sum of two integers again an integer. Okay, so again let's prove this. So what's given? A divides b. So there is some integer k such that it's always abbreviated to s dot t. B can be written as ka. We know that a divides c. So there's an integer L such that C can be written as L times A. And now what we want is to somehow look at the number B plus C. Okay. Now I'm just going to skip the writing this on the margin, and let's just try and work this out directly. I need to somehow understand what B plus C looks like. Right. So I'll just do the following. I will add these two equations. And so I get it's Ka plus La. So it's K plus L times A. Okay, and that's exactly the kind of thing we need, because now if K and L are integers, then K plus L is again some other integer. So let's call that M. Let M denote the sum of K and L. That's an integer. And what we have just proved is that B plus C can be written as M times A. So that means that A divides B plus C. Okay, so that is the proof. Okay, now what has all this got to do with our currencies and being able to pay using just two currencies? So here's the statement. So sometimes, when we make mathematical statements, we give them various names as lemma or proposition and so on. Here's a little statement which we will call a lemma. So a lemma is just a sort of a minor mathematical statement, a small statement which we can prove rather easily, but which often gets used again and again in, say, larger proofs or bigger statements and so on. So here's a little lemma. It says that if A divides B, so let A be C, let me say again, let A B and C, the integers. If A divides both B and C, then A also divides every number of the form m times A, some multiple of A, plus n times B, which is some multiple of B. And what are m and n here? For all integers m and n. Okay, so what this statement says is pick any integer m and n, then construct the number m times A plus n times B, then m times B plus n times C, then A will also divide that number. Okay, so let's prove this. Again, one other aspect of mathematical proof is once you have proved a set of earlier statements and then you want to try and prove something later on, you don't always need to start from scratch and prove this statement. And we could also do it like that. We can give a similar proof like the ones we did earlier. But since we have already proved a few earlier statements, we can use them to prove this next statement. So let me show you what I mean. So observe, we already proved the following. So if A divides B, then okay, and so observe the following. We know this. We are given this. We know that A divides B. Now what we already also know is that B certainly divides a multiple of B. Okay, B certainly divides m times B by definition, right? And we already proved this. If A divides B and B divides C, then it means that A divides C. So we already proved this statement. So therefore, by using what we already proved, we conclude that this and this fact together tell you that A divides MB. Okay, likewise, A is given to divide C, and we know just from definition that C always divides any multiple of C. C divides NC. And we have proved earlier that if this happens, then A divides the very n. Okay, and now remember, we also proved another statement which said, so let's see these two things here. A divides MB, A divides NC, and we just proved a statement which said that if this happens, then A also divides the sum of those two numbers. Okay, and that's exactly what we need to do. So this is the other important thing with lots of proofs. You don't always want to start from scratch and reprove every new statement. You want to be able to use statements that you have proved earlier to simplify your work to some extent.
This reminds me of 16 and 10 rupee coins.
Right.
So if you take B to be 16 and C to be 10,
right,
then you're saying that MB plus NC is some quantity you can pay.
Right.
And what this is saying is that that's always going to be divisible by 2 because 2 divides 16 and 2 divides 10.
Absolutely. So that's the reason why we looked at this. So suppose I take B to be the number 16 and C to be the number 10, then what are all the transactions I can do just using these two coins? Well, I can give you some number of 16 rupee coins or take some number of 16 rupee coins from you. So that is some integer m times 16 and plus n times a 10 rupee coin. Okay, look at all these possibilities where m and n now can be integers, meaning they can be either positive numbers or negative numbers.
Or 0.
Or 0. So positive means I am giving you a coin, those many coins. Negative just means I am taking those coins from you. So these are all the possible transactions we can perform using only 16 and 10 rupee coins. And what we just concluded there is the following. So look at the number A equals 2. Okay, 2 divides both these numbers. So observe, 2 divides 10 and 2 divides 16. And so by what we just said, this implies 2 will always divide any number of the form MB plus NC. So if you take m times 16 plus n times 10, then 2 is always going to divide that. Okay, and therefore the only things I can pay, anything I can pay using these two coins will always be a multiple of